Hello Math 2413 students, here's lesson 7, parametric differentiation. Do you recall vector functions from lesson 1 way back? A vector is basically a pair of real numbers, x comma y. That's two-dimensional vector. If you have three-dimensional vector, then you're going to get a triple, x comma y comma z. We are in calculus 1, so let's take to just planar case, the two-dimensional case, x comma y only. Now, if both x and y depend upon a time variable t, then you're going to consider this vector p of t is changing with respect to time. And x-coordinate is changing, that's x of t, and y-coordinate is also changing, that's y of t. Put together, you get a vector function. In a special case, when the vector function is a position vector, then it is visualized as a parametric curve. I'll show you in a moment. Oops, sorry about that. I wanted to open this one. Here's a simple case. P of t is x of t comma y of t, and x of t is a linear function, x0 plus at, and y of t is also linear, y0 plus bt. Both are linear. And then it ends up creating a line like this, highlighted in purple. And I'm not surprised because both x and y coordinates are linear, so it must be a line. Let's see, let's check. Indeed, this is what we are getting. So t is time. As t changes, the position vector moves around. Let's stop here. T is about -2.25. Position vector is right over here. And starting from the origin, points toward the position of the point. And then that's moving around. And then if you consider the trace of the position vector, you get the line. So that's an example of a position vector function. And trace of the position vector function from t moving from somewhere to somewhere, say t1 to t2, represent a parametric curve. And the example I just showed you gave you a line. Next example here, you're going to get an ellipse. Let's run it again. All right. And then here, a and b values are randomized. x0 and y0 values are a bit randomized too. What we end up with an ellipse centered at x0, y0, and then major radius of a and minor radius of b. That is, from the center all the way to the horizontal end is a, and from the center all the way to vertical end is b. So major radius horizontally, minor radius b, and those values are like these. And then time t is going from 0 to 2 pi. We have trig functions, so we want to have entire period. So from 0 to 2 pi, and then let's move it around. What do you see? The trace of the position vector. The tip of this arrow is where the position vector is pointing toward. And you can consider that as a moving point. So a point is moving along this curve. Or the trace of this position vector is giving you a curve. And that kind of curve is called a parametric curve. Here, x of t is like this, y of t is like that. Let's see another example. Okay, this time a little bit hard to follow, but it's going to be aesthetically beautiful. X of t is rather complicated, y of t is also rather complicated, but all these are sines and cosines, so you can clearly consider this as a periodic. So we have a closed curve, and here we go. It looks pretty. I named it flower, and let's run it with animation. Let's see. Oh, too fast. So the point is moving around. And then position vector also follows the point. What's the position vector? the arrow starting from the origin pointing toward the point. So you can consider this as the trace of moving point, or you can consider it as the trace of moving arrow, the tip of the arrow, position vector. So if you look at it as a point, then it's red dot moving around. If you consider it as position vector function, then the arrows are moving around, but the end result is the same. You get a curve. And in this particular case, time t is going from 0 to 4 pi. Another example, okay, all right, that's a flower, and this one is called butterfly, and x of t is like this and y of t is like that. Again, we have a periodic function, just sine and cosine. And then let's run it again. Okay, let's run the animation. Again, similar situation. A red dot is moving around. So if you consider a dot, a point is moving around versus the position vector, tip of the arrow is moving around, either way you get the same thing. The end result is a curve, a closed curve that looks like kind of like a butterfly. So in short, if you have a pair of functions, x of t and y of t, put together you get a position vector function, and that defines a curve. Now let's do some calculus with this curve. Find the derivative. How do you do that? Well, we can define the derivative using Newton quotient like this. You can divide by h because h is scalar, just a real number, so it's the same as multiplying by 1 over h, no problem there. And then take the limit, you're going to get the instantaneous rate of change, which we call the derivative. It's a vector, so it's a derivative vector. Some people call it velocity vector. And it turns out that if you have a derivative vector of this vector function, that's nothing more than a pair of derivative functions, x prime of t comma y prime of t. You can actually rigorously prove it using Newton quotient, passing on to each component, but I'm not going to emphasize the proof part too much in this course. The proof is here, but I'm not going to overemphasize it. If you're following it, great. Otherwise, it's okay. Just remember the result. The derivative computation, how do you do that? Are you going to use Newton quotient? No. You're going to use the derivative formulas for x and y, respectively. By the way, how can we visualize a derivative? Well, it turns out the derivative is the instantaneous rate of change, and in this case, the point is moving around a circle, not necessarily a circle, excuse me, a curve, and then instantaneous rate of change points towards the direction and magnitude of the motion. So what do you end up with? We end up with these kind of arrows. The length of the arrow represents the speed. And then the direction is, well, direction of the arrow is direction of the motion. So this derivative vector represented like these arrows, those are, as a matter of fact, velocity vectors as the point move along this curve. Okay, I don't want to go too much into physics. Let's do some math problems instead. Ooh, I have some more. Okay, all right. There's some more pretty pictures here. Okay, apparently there is. Okay, I'll show you some. All right. The red arrow is the derivative vector. And then blue dot is moving along the curve. In this case, the curve is line. And please note that red vector is constant, the same. And not coincidentally, the dot is moving along with no change of direction and no change of speed. Okay, all right. How about the next example? Ellipse? Okay, all right. Let's see it. It's a little bit hard to see because this one looks almost circular. Let's try this again with a little bit more elongated. Okay, all right. In this case, you will see the lengths of arrows will change accordingly. And please note that the dot is moving relatively faster when the arrow is longer, and then it kind of slows down when the arrow gets shorter. See that? Let's see, do we have a couple more? I don't know whether this is worthy, but whew. Okay, all right. And the red arrow here is the velocity vector, the derivative vector. So it represents the speed and direction of the motion. And then it changes rather radically. And then the dot sometimes moves quickly and sometimes it slows down. And that corresponds to the length of the arrow. One final example, and then we are going to go ahead with some computation problems. Let's see, how about the butterfly example? Again, pretty much the same. The red arrow, the derivative vector, sometimes gets longer, sometimes gets smaller. And then when it's long, that means this dot is moving quickly there. And then when the arrow gets smaller, that means it's tentatively slowing down. Okay, all right. So we enter some visualizations. But then again, those are merely for fun. As for some math exercises, okay, here we go. Calculate the given derivative vector. So all right, let's calculate the derivative. How do you do that? Do we set up Newton quotient and find out the limit the way it is defined like this? Of course not, we don't do it that way. We do it this way. Take the derivative of x and derivative of y separately and put those two together. Simple derivative computation, so let's go ahead. Take the derivative, we get this by product rule. Excuse me, it's not a product rule, it's just a power rule and exponential function. And then the second derivative here, the derivative of the second component, y prime, that's a product rule. So here's a derivative vector. So when you have a vector function, basically you have two derivative computations because you have x, you have y. Those are two separate functions, so we have two derivative computation. Now if you have 3D vector in 3D space, in that case you're going to get some curve in 3D space. You have three derivative computations to do. In 4D it's even worse. Let's see, how about the second? Solution 2. What's the difference between solution 1 and solution 2? They're the same. I just did the derivative computation. It's just single step. How about this one here? The derivative computation. Cosine of t squared plus t, sine of t squared plus t. Start to play back and try on your own. It's just a chain rule problem. So what is it? Take the derivative. Okay, sine becomes cosine. You have to multiply the derivative of the inside. So put together, we get this. Or you can do the computation at the same time. Just take the derivative of this, using chain rule here. Derivative of that, we get this, using the chain rule. Again, just chain rule problem. How about the next example here? Oh, we have scalar multiplication, but scalar is also changing. So you can use either product rule, or you can just distribute and calculate the derivative of x and derivative of y separately. Let's see. X is t squared plus t times cosine of t. Calculate the derivative using the product rule. Same here, product rule. And then you can put together. Easy.